So, welcome everybody to the PTV Viswalk Pedestrian Simulation webinar. My name is Tobias Kretz. I'm the PTV's product manager for Viswalk. And next to me here in the office is my colleague Sven Beller, who during the presentation will reply to your chat questions. So you can ask questions in the chat. I will first talk shortly about the scope of Viswalk applications and then demonstrate the typical workflow in a very basic, very simple model, and then later step by step highlight some of the features of Viswalk without going into all details, which we obviously cannot do today in these 30 minutes. If you see here, item 6, behavior models, means that we will have a look at the foundations of the model of operational dynamics as well as how route choices can be modeled, so the tactical layer of the pedestrian dynamics. Of course, in the next 30 minutes I can address each issue only very briefly. However, Sven and I will be available after the webinar to answer your questions in the chat. Maybe some of you already have attended the PTV Vissim webinar last week, simulation of road traffic. Road traffic as a term describes a subsystem of our daily life which has a clear definition, clear boundaries which distinguish it from the rest of our life. However, walking is very common in very many, very different parts of our everyday life and cannot be seen as clearly distinguished from all of our life as road traffic maybe can be. So what is Viswalk about? Our aim is that PTV Viswalk covers all situations where people are walking and long for a destination. So with Viswalk you can add benefit in a planning process for such situations when people move on their feet and long for a destination. This needs to be distinguished from some other situations where walking or moving is a purpose of its own, which is most obvious for example, for dancing or practicing sports. So this is outside the scope of Viswalk. That is maybe the simplest definition you can give to set the boundaries of the scope of Viswalk. Here are 4 examples for the scope of application: station planning, traffic and urban planning, event planning, and fire safety engineering. And so let's have a look at the software itself. And create a small model. The essential basic elements that you need to create a model are areas where the pedestrians walk on, and then inputs, so you define the demand, and the routes where the pedestrians are walking on. And so I will start with the areas and create a base area about 20 meters long. And you see there was a dialog for the areas, and you can also see the properties of this area, or some of the properties in the list here. You can configure the list view with this dialog and show more properties. So that's totally up to you what you want to have listed in the list. And apart from this base area, we need some more areas, or 2 more areas. One as an area where pedestrians will be set into the simulation. I'll create it to the left. And another area to the right, which will serve as the destination. So that's the geometry. For those of you who know Vissim already, are very familiar, of course, with the concept of links and connectors, so that there are two elements to create the geometric structure where the dynamics is taking place. For pedestrians, there is nothing like connectors. So what you have to do is to make the areas overlap, and that's it then. So the next element will be just one route, which means for our pedestrians, there will be no real route choice, but they will follow all this one route. I will later on show a little bit of the real functionality of the routes in a little bit more complex model. But for now, let's stick with one route. And then we need an input, which is just marked with another dot. And we have to define the strength of this input. And let's say we want 5,000 pedestrians here. Good. That's it already, and we can run the simulation. Here you see the pedestrians walking, and we can also follow this in 3D. You might realize already in 3D it's a bit slower than in 2D. That's totally up to the graphics card, what it can handle better. You see here at the bottom of the screen, currently it's 5.1. That's the factor, how fast it is compared to real-time speed. And when I go here to the quick mode, you see without display, the simulation can proceed much, much faster, 180 times as fast as reality, which means it's about now 35 to 40 times as fast as with animation turned on. Just to point out the factors which determine the runtime. The next I want to show a little bit is one example of measurements that can be done in Viswalk. And for that I will create a measurement area, which has the general name section now. Let's have a rectangle, and I will create it here somewhere in the center. And you can see it now with this blue edge. And now I need to make from this measurement area an area measurement. That might seem a little bit complicated, but in this way you can combine two measurement areas to be one area measurement. For our simple model, that's not necessary. We need from one measurement area to create one area measurement, and that's done here. And now we need to define the settings for this area measurement. That's done in this dialog, evaluation, configuration, and then first we have to activate it, and we want a time interval of 300 seconds. Okay. And we want as a result an average of 10 simulation runs, so that it's not only one simulation run that contributes to the result, but 10. And to not generate too many data, that the lists become too long, we want to limit the runtime to 1,200 seconds. Okay, so let's go. Pedestrians are walking, and of course it would take quite long now if we wait for all of the 10 simulations watching the pedestrians. So let's go to quick mode and let's have a look at the results. Here is the list of results, and you can see in this list of results that whenever a new simulation starts, the full set of lines is inserted for all of the time intervals. In each simulation run we have 4 time intervals now, and whenever a time interval is concluded, you can see the results here. In quick mode, the lists are not updated as frequently as in the normal mode, so also there some time is saved, but it's going quite fast. Apart from the results of each individual time interval, you can see some functions, averaging or finding the minimum or maximum within the time interval. So here we have the average number of pedestrians on the area over all of the time intervals. And what is also possible is to show at the end of the list a function for all of the time intervals which is then an average or a function over all of the simulation runs. So here, this number here tells us it's the average for the first time interval over all of the simulation runs which have been done so far. And of course you can also combine it, and you have the average over time intervals and also average over simulation runs. And that is all kept within the within Viswalk itself. You can of course export it to a file, and you can copy and paste it, for example, to Excel. Good, our 10 simulation runs are finished already, and we could now work with the results. But what I want to show you now is to expand the model a little bit, create a second input, also with 5,000 pedestrians, and also a second route for these new pedestrians here. And let me just go back and have only one simulation run, just to have a model where there is also a bit more than just a trivial dynamics. And even with these low volumes of pedestrians and in the simple model, you can already see how spontaneously these famous lanes of pedestrians in bidirectional flow are emerging. And I can, during the simulation run, double the volumes, and we now have more pedestrians, which typically will fortify the lanes which are emerging because they are more stable as there's more pedestrians in each of the lanes. And we can do it so, if we do it a second time, I guess at some time a jam will evolve, and then in the end we can reduce it again. And any jam will dissolve. Good. So much for this very simple, very basic example. What I want to do now is go to a model which I have prepared already and talk a little bit about this one. You see here there is some building structure, I call it a hotel sometimes, is already created, and what you also see is that there is now two network editor windows which show the same model. And what is interesting here, you can, for example, select a wall here, and it will also be selected in the 2D window. So I select another wall in the 3D window, in the 3D view, and it will be selected also in the other network editor window, which shows the 2D view. And when I modify the wall in 2D, it will be modified in 3D as well. I'll undo this. That is, of course, very helpful to create a model like this one, where the same or very similar geometry exists in very many floors, and in this way you can always select the correct element and work with the correct element and at the same time have a check. So for example, I would select here the wrong element. I intend to grab this one, but I get the wrong one. I see immediately I've done a mistake. Let's first have a look how this simulation looks like without any modifications. You see here in the 2D view the pedestrians and the geometry of all floors put one over the other. Therefore, it looks very crowded here. You can, of course, turn off the display of pedestrians in the higher floors or in all floors, or only show the higher floor to have a better overview. So that's fully flexible. And the pedestrians walk out of the building, and when they have reached a safe space, they are taken out of the simulation. Now, the next thing I want to show you is a bit of our level of service display. For this, I first have to activate it generally here and set a time interval of maybe 30 seconds. Okay. And activate the level of service display for our areas. Use color scheme, yes. First we will have a look at it for the areas only, and I want to see the density for the current run and the last completed time interval. And let's use the level of service scheme from Weidmann, because it has many levels and many colors, therefore, which is best suited to demonstrate this. I also have to set it here for the other network window. Just the same steps: density, current run, last completed, and Weidmann, apply OK. So we see the same in both network windows. That implies that if you want, you can see different things in both network windows. And as the simulation proceeds, maybe in our 2D view, let's only watch the ground floor. As soon as we have 30 seconds reached, the level of service should be shown. Of course, it's not possible to show it before the first time interval has been concluded. Here we are, and it's also shown in 3D. Maybe we have a better idea of it like this. And it's up to you to show the pedestrians along with the level of service or to hide them. And the same here. Good. This level of service, which is shown on full areas, your areas, which you have created as a user, is only one option. The other option is to show it on grid cells. And here, let's also have a look at the density. And then it looks like this. Again, it will take 30 seconds before you see the first results. It will take one time interval, and then you will have a level of service display which is much more fine-grained than before when it was shown on the areas. So that's two different options you have, and they produce these different results. You can imagine that if you choose a long time interval, these maps look completely different than when you choose a very short time interval. You can go down with the time interval to 1 second, and then of course it will always show just the floor highlighted under a pedestrian. So also here you can show and hide the pedestrians, of course. What is also possible is to see a list of pedestrians, which you also could export to Excel when you pause the simulation. You could just copy and paste it. Good. So much for this model where only pedestrians were walking. I'm sure nearly all of you have heard that Viswalk is fully integrated with Vissim, our well-known vehicle simulation. And so, of course, the natural next step is to add some vehicles to the scenario, to the model, which I've done already here. So there's just a road here, and the pedestrians will just walk from the same model as before, and their final destination is just replaced to a spot on the other side of the road. And let's see what's going to happen now when we run the simulation with this very simple extension of just adding a road. Here we have a car, and there the pedestrians are coming, and what is going to happen is, boom, the car does not stop. So we have to do a little bit more to achieve a realistic combination of pedestrian and vehicular traffic. And for this I have to show the vehicle objects in my network objects bar here. And the only thing we have to do after we have added the infrastructure for both the pedestrians and the vehicles is to define at the conflict areas who should have the right of way. And I said it for once now that the cars have the right of way, which you can recognize here that the car link, the vehicular link here is in the direction of the vehicular link you have the green color, and in the direction of the pedestrian walking area, pedestrian link, you have a red area. So now the pedestrians stop for cars when cars are approaching, and they will proceed only if there is a sufficient gap between two cars. This is implemented such that when a car is still too far away that it could be seen by pedestrians, and pedestrians are slowed down by other pedestrians, so it takes them longer that they can pass the road than they expected, then the cars have to stop, obviously, although they have the right of way, and they do stop. They do not run over the pedestrians, which is obviously realistic. And you see that there is now quite a complex interrelation between pedestrians and vehicles. But hopefully, when there is really an emergency evacuation going on, the cars will leave the right of way to pedestrians, even if there is no pedestrian precinct here. So let's change it and look how it looks now when the pedestrians have the right of way. And now it's quite clear there is a continuous flow of pedestrians, and the cars will only proceed later when the last pedestrian has crossed the road. And as the pedestrians have the right of way now, there is no reason for them to stop, and there are so many of them there that there is of course no gap. So they just continue walking. Good. So that's it for the combination with vehicles. What I have also prepared for you is a combination with the public transport simulation, and that's the model here. I also run it without having changed the relevant elements. I've just added the train here, the tram, and I have added or increased the platform edge area here. So the pedestrians watch this guy, what will happen when he reaches the area. That's the destination of his route. What is he going to do? He disappears. So we have to do one more step to really connect the pedestrian simulation to the public transport simulation, and that is that we have to tell that area, which is the route destination for the pedestrians, that it is a waiting area for public transport. Okay, now run the simulation. See what happens. I will just turn off the display here in 3D because it takes some time to display the doors opening and closing, and that slows down the display of the simulation. So let's just follow it in 2D. And you see when the scheduled departure time of the train has come, the doors are closing and the pedestrians distribute now on the waiting area and will wait for the next train, which is approaching here. You see the pedestrians who have alighted here. Let's think of them as firefighters. They are waiting here for the last evacuees to come out of the building. Again, we have a bidirectional flow here on the crossing area as before in the simple model. This waiting area, I've created it here for a purpose to demonstrate for you the waiting behavior in an unorganized manner. Later you will also see organized queuing areas. So the last pedestrians walk out of the building, and now the pedestrians who have arrived walk into the building and distribute. Whenever they reach a room, their destined room, their destination, they disappear. They are taken out of the simulation. Okay, so that was the part where I wanted to demonstrate you these features: a basic model, a model with a bit more complex pedestrian infrastructure, a model including vehicles, a model including public transport. Now let's go back to the presentation and talk a bit about the behavior models. I want to do that for the operational level, the tactical level, and I call it intermediate level, which is arguably precise or not. The operational level is mainly handled by the social force model, which is a model where the first computed property of movement is acceleration, and then via integration we have the speed, the velocity, and then with a second integration step we have the new position of the pedestrian. The force which acts on a pedestrian comprises of the driving force, forces from other pedestrians, and forces from obstacles. To explain you one element, the driving force, a bit more in detail, I have here an animation which visualizes the computation process internally when the simulation is started and a pedestrian is heading for a destination. Here it would be this spot here, an exit. A field is computed, a map of distances, and in this map of distances the gradients, the negative gradients, can be computed, which are orthogonal to the lines of equal distance to destination. And if the pedestrians follow the negative gradients to destination, they will walk on the shortest path to destination under consideration of the obstacles. So this negative gradient of this field of distances is used as the direction of the desired velocity, where you as a user set the absolute value, the desired speed. The forces between pedestrians are basically distance-based. We have two components for the force between pedestrians, which are just summed up. One of the forces is dependent on the relative speed between the two pedestrians in addition to the distance. It's a bit more complicated formula. Just send me a mail if you want to know the details about this. It's too complicated here for the webinar. I think I would need more time to explain this. Of course, pedestrians are no particles, no physical particles. There is no conservation of momentum, no conservation of energy, and there is no actio equals reactio like in Newton's physics, but a pedestrian or something which happens in front, what the pedestrian sees, has a much stronger impact on a pedestrian than what happens in the back. And that can be controlled with a parameter lambda. If it is 0, something that happens in the back has no impact at all on this pedestrian, and then between the angles there's just a linear interpolation. And if you set this lambda to 1, which is not realistic, the effects from all directions have the same effect. Here is one animation which shows something where the social force model is particularly strong, namely the creation of these emergently forming lanes of pedestrians who are in a bidirectional flow situation. And you can see here that some pedestrians have to go diagonally from the right or the top side to the bottom side from your perspective, and others have go in opposite directions. So their trajectories have to cross, and in this scenario this means that these lanes which exist, they have to dissolve at some time, you see it here, and then they have to reform at some later time. And that quickly enough, else a deadlock will form soon. So much for the social force model and the operational level. Now a little bit on the tactical level. For that I have to go to Vissim once more. We are here, I think. No, that was the wrong Vissim. I want to go to this one. Tactical level now means that I want to show you a little bit about the routes concept. We have here pedestrians walking in this scenario, and they have to decide for one of the two exits, and that is just handled with two routes, main routes, which end at these two destinations. And by changing the relative flow, I can make pedestrians all going to one side, or I can make them all going to the other side, or I can choose any relation in between, 3 going to the bottom, 1 going to the upper side. Now, with these main routes, which implicitly, together with the input, define the OD matrix, there would be some difficulties if only these main routes would exist, because sometimes you have large main routes going over some hundreds of meters, and in between maybe some counter, some desk, where you have to do a rerouting on very small areas. And for this we have come up with the concept of partial routes, and you see here a partial route decision where two partial routes are attached, and one of the two partial routes is going to this area in front of this display here. And so far only that partial route which is not going to the display had a relative flow, and I will change this now such that also the other one has a relative flow. And now half of the pedestrians choose to go and watch this display here, which is just a red wall in this case, but that doesn't matter. And they wait there for something 20 plus minus 2 seconds. It's a normal distribution in this case, and then they proceed with their way. And you see that now the pedestrians who are here, they also distribute to both sides, to the lower side or to the upper side. I can change that by just replacing the destination of the partial routes, and then the other destination is changed as well. And now only pedestrians who have this destination as their main destination will walk in front of that display. That is because pedestrians only react to our partial routes when they lead back to their main route. In this way, first, the OD matrix is preserved, and second, we can make our partial routes destination dependent. Yeah, I have now changed it back, and you see again pedestrians continuing from here choose both destinations again. What is also possible is to make these partial routes class dependent. So here I now choose that only men should walk to the display. We only can see this in 3D. Yeah, that's obviously so far only men, and we need some more time that you really believe it, that it's only men. And I can change it that it's only women. So of course some men are still waiting, but now new pedestrians coming here are all women. That's not a concept of gender, but it's a generic concept of classes. I can also make only people with green hair to go in front of the display, so maybe it's a specific type of hair dye which is sold here and shown in the display. Only the blue haired people, no matter if it's men or women. And I can also say it should be only the people with natural hair color who come to the display. So that concept of the partial routes, it's class dependent and it's destination dependent, and you can use it easily such that it preserves the OD matrix, which is something which you normally will want to have as a planner. Good. Such partial routes where you have these static route choice ratios are not the entire story, but we also have partial routes which depend on the load of routes in front, and here I will just increase the input here, and you see whenever a pedestrian is walking here over this area with the partial route choice, the pedestrian continues to head for that queuing area which is currently the shortest one and which is closer to him if there is two queues which have the same length. The shape of the queue can be determined with 2 parameters, so you can make them very straight and very ordered, or very disordered and disorganized. That's both is possible. And it's also possible, you can see it already to the right, to have not such an area here as you would model a supermarket and the choice for a cashier, but here, like let's say immigration in an airport is organized. Often you have one main route and then a number of fork type queues or queues where the service desks are actually. And you can of course set with a parameter the number of pedestrians who should be placed in the queues in front of the service desks. Good. So back to the presentation. The final thing I would like to demonstrate to you is our dynamic potential. And I'd like to do this at first also within Viswalk. And just watch these two simulations here, or not simulations, it's one simulation, but two separate areas where pedestrians are walking. And this group of each 500 pedestrians, they have to walk around this corner and end up here at this destination area. And at first, it looks very similar how they are walking, but then you realize more and more that they are cramming here on the left side very much around the corner. And here, the density around the corner stays limited at a much lower level, and the pedestrians walk a larger radius. And of course, they do some meters in addition, but still they arrive earlier at the destination. You will see it in the end that the right group, the last person of the right group, ends up at the destination much earlier than on the left side. And the reason for this is rooted in what I've shown you before, that in the simple approach, what is computed is a map of distance to destination. And the assumption is that pedestrians basically, before effects from other pedestrians are added, pedestrians basically want to walk into the direction of the shortest path. So fewest meters to destination. On the right side, the assumption is that pedestrians want to arrive as early as possible. So it's the basic assumption which you make in traffic planning when you do an assignment computation with Visum or Vissim or whatever. And that's, of course, very accepted for vehicles, but the travel time, let's say, it plays at least some role also for pedestrians. And in some situations, like when you're late for a train at a station, it's the most important factor, travel time. You want to arrive as early as possible, and that's your determining paradigm for movement. And so our solution, which we offer here, is called the dynamic potential, and you can see it in two dimensions. Whenever a route destination point is shown as a square, then the dynamic potential is active. You also can see it in the list. Use dynamic potential, yes. And for the other route here, this is not activated. And then there is two parameters where the computation depends on. And so with this method, you can change between distance-oriented and travel time-oriented behavior in the simulation. So here, let's see, we are now at simulation second 165, I guess, when this pedestrian arrives here. And now let's wait for the end of the simulation on the left side, and it takes quite some time. So we have now done 40 more seconds, 50 more, 60 more, and about 70 more seconds until the left side has ended. And it was the same number of pedestrians on both sides. So let's see in the presentation how this is, what is the reason for this. And that's visualized here in this video, which, by the way, is also in our YouTube channel, where here some pedestrians are walking through this door, and there is a red pedestrian coming here. And normally the way through this gate here was shorter to arrive here at the green area. And here going this way is a bit longer, but there is no other pedestrians here. So the next red pedestrian who will end up here will decide to go the other direction, because then there is some more blue pedestrians here making the estimated remaining travel time longer through the storm. And so he's now turning around and going to the other direction. And mathematically what is done is just as before, when a map of distances was computed. Now whenever this wave which is sent out in the mathematical computation is flowing over the spot of a pedestrian, it's a bit retarded. It takes a bit longer. And you see here when it's going over this spot with the jam, with the blue pedestrians, it's much delayed. And then the two waves arrive about at the same time here at the spot where the red pedestrians arrive. And that offers the possibility to route pedestrians dynamically through one of the two doors, depending on how large a jam is here. And that has effects on many situations, like a corner here in this scenario. You've seen it before in the simulation. It also has an effect on bidirectional situations, and that's very much pronounced in this situation here, where there is counterflow at the corner. So the combination of both, where it doesn't really work when you make pedestrians head for the shortest path to destination, but when they're always thinking, what can I do that I arrive as early as possible at the destination, then these lanes which form with the social force model, they are perceived or they are kept in the counterflow situation at the corner as well. And here at some time they collapse, at least on the inner side here, and that the two groups to 60, 70 and more percent block each other. And here there is never a deadlock. And that's a situation. It's quite a short example, a laboratory example. It never happens in reality, but it makes quite clear what this method does. When of these 72 pedestrians, each has to go exactly to the opposite spot, and that's much more realistic simulated with this dynamic potential. Good. So as a summary, Viswalk, or why should you use Viswalk? Viswalk includes modeling, simulation, and analysis in one single environment. Viswalk has a GUI made for efficient and fail-safe modeling. You see what you do quickly, immediately, and you do not miss any mistake, which always happens. Viswalk is the most advanced pedestrian simulation in terms of the basic pedestrian dynamics algorithms. I'm referring here very much to the dynamic potential. Viswalk has a large set of functionalities to model behavior on the tactical level. That's the point where I could really not show you everything that we have available in this short time. Viswalk is fully integrated with PTV Vissim road traffic simulation and public transport simulation. Viswalk is very efficiently in simulating. I had 20,000 pedestrians in real time, for example, and I successfully tested Viswalk with 5 million pedestrians, which of course takes some time to do the simulation, but it is possible to do it. Viswalk has a 2D and a 3D mode available at all times during modeling, simulation, and analysis. You can have both at the same time, and you can change any time between the two. Viswalk has a flexible time resolution of 1 to 20 simulation steps per simulation second, which means that you can do quite quick simulations with only 1 or 2 simulation steps per simulation second. And with 20 steps you can do, for example, which is the next point, very nice video recordings, as it's quite a high time resolution which is required to create good videos where someone watching it really sees what's going on and not is confused by a too small time step. And finally, Viswalk is not a black box. All core algorithms are published in peer-reviewed scientific journals, and just contact me if you are interested to have these papers. Then finally, some further information. We have training courses. So if today this all was too fast and not everything you need, we have a training course for Viswalk which takes 1 day. And these training courses are regularly held in Karlsruhe. The next one is on May 22nd, next English one, and on your request. We also come to your office if you have no other chance to organize it. There is a web page, of course, specifically on our training opportunities, also in other spots, not only Karlsruhe. So that's this URL here. Then we have some more online resources. Of course, there is a Viswalk homepage, no doubt. There is also a PTV Vision YouTube channel with a lot of Viswalk content. A number of the videos which I've shown today to you are available there. Also watch out for the explanations which are given in the description under the video. We have taken a lot of care that these really add benefit to the video there. So it's not only graphical content which is displayed in the YouTube channel. And there is not only videos from us, but there is also a PTV Viswalk playlist at YouTube, which also includes content which our clients have uploaded to YouTube. There is a demo version of PTV Viswalk. There is a blog for PTV Vision. And PTV as a company, of course, has also a customer magazine. In the next few weeks, we have some more webinars coming up in English language. The next 3 are on public transport, emission modeling with Vissim, and the simulation of active traffic management. So watch out for these if you are interested in these topics. There are also some webinars on PTV Visum, quite a number of these. And yeah, finally, maybe you have the opportunity to come to our users group meeting. I would be happy to also get introduced to you personally after this webinar. It's the users group meeting is May 26th to 28th, and this year it will take place in Berlin. And here is a link for you. That's it. Thank you for joining this webinar, and as I said, we are now happy to answer further questions.